Welcome to this latest video in our series on doing things with geometric algebra. In this video, we'll solve this problem that was presented on the channel Mind Your Decisions, which I hope you'll check out because they present a lot of really neat problems. So in this one, we're given a quarter circle and a semicircle that's inscribed therein, and this dimension 1, and we're asked to find out what fraction is the red area here of the quarter circle. Now, at first glance, the statement of this problem seems incomplete. How can we solve it if all we know is this dimension? And we seem to have been given insufficient data. I played around with this a little bit, then decided to work instead on a more general version. And viewers may recognize that I was acting upon the so-called inventor's paradox, which is stated in different ways. This is how George Polya stated it, and you may recognize his name as the author of the classic book, How to Solve It. I'll let you read that for a few seconds here. What he's getting at, and as other people have stated it, there are times when, if we're given a problem, we will actually find it easier to solve a problem that's more general than the one that we're given. So that's really what I was doing here, or that's what we'll see me doing here in just a moment. So what is the more general problem that I decided to work on? It's this one. Given this quarter circle and the inscribed semicircle, what is the radius of the semicircle if I choose this direction of a radius from the center of the quarter circle? So given r hat here, what will be the radius of the semicircle that's tangent internally to the quarter circle? And also, what are the coordinates of these endpoints? So the way I formulated this problem is here. You can see that I defined u hat and u hat I, which we will be using only near the end of this video. And here is the direction of r hat. And also I've defined a vector v hat from the center of the semicircle out to the points of intersection here. So big R is the radius of the quarter circle. Little r is the radius of the semicircle. So how do we solve this? Well, the main thing we're going to notice here is that these two sides, and therefore these two vectors, are perpendicular. So if we take their inner product, or the inner product of these two vectors, the inner product will be equal to 0. And if we take that inner product here and fight through all this, then when the smoke clears, we find that little r is equal to big R, or is equal to 1/2 big R. So there is no dependence upon the direction of r hat, which means that no matter what direction we choose for r hat, the semicircle's radius is half of big R here. Now, before we go too far, of course, we want to check and see if this is correct. So here is a GeoGebra construction that will allow us to check that. We'll vary r hat here, and we'll see that this radius is always 3. Even when we go down to here, it's half of big R. Whoops, there it disappeared. So the answer is correct, and that's kind of interesting. What that shows is that back on our problem statement, the general problem, or the original problem statement, this dimension 1 was not insufficient as I had thought. It's actually superfluous. It doesn't matter where or how this semicircle is aligned inside the quarter circle. Its area will always be 1/4 of the area of the quarter circle. So that's kind of interesting. Now back to our more general problem. We also want to know the endpoints. So knowing that the radius of the semicircle is half the radius of the quarter circle, that means that this distance out to here is just big R, or I should explain it a little better. We know that the radius of the semicircle is R over 2, so this distance here is twice the projection of this one upon u hat. So in other words too, it's the projection of twice this distance upon u hat, or big R times r hat dot u hat. And similarly, this distance to this intersection point, or this end point of the diameter, is big R times r hat dot u hat I. So I hope that this problem's been interesting, and I hope too that you'll consider joining the Pre-University Geometric Algebra group on LinkedIn. Your participation will be welcome, and I'll link this group also in the video description. Thank you for your time, and I look forward to your comments, and I hope improvements.